Okay. So yeah, it's so welcome everybody to the second one world probability seminar this term. So it's a great pleasure, great honor to have Chris Lutsko and Balint Toth speaking today about invariance principles for the random Lorentz gas beyond kinetic timescales. So Chris, stage is yours.
All right. So thank you very much for the introduction. And let me say that I think Balint and I were both very excited to receive this invitation. So thank you very much to the organizers. So both Balint and I will be talking about this general program of understanding diffusion from microscopic particle dynamics. And we're both going to focus on what is perhaps one of the simplest models of particle dynamics, but still highly non-trivial, which is the Lorentz gas. So this was introduced in 1906 by Lorentz, and he wanted to study the flow of electrons through metals. So let me explain the model. We have a point set in RD, and we're going to place spherical scatterers on this point set. And then we let our process xr of t denote the position at time t of a particle starting at the origin and colliding elastically with the scattering set. So here I have two examples. One is where the point set is a Poisson process, and one is where the point set is periodic. So we see the motion of this particle, and notice that we have kind of non-Markovian behavior when the particle sees this scatterer twice, for example. Okay. Throughout my talk, at least, these scatterers will have infinite mass, so they will remain stationary, and the scattering potential is hard, right? So now the holy grail in this area is to establish a central limit theorem in the diffusive scaling. So we normalize by square root t, and we expect the position to behave like a Gaussian. And even better is an invariance principle, so convergence along paths, right? So we have convergence and distribution of the whole path to a Wiener process. So this is the holy grail. And in particular, it fits in with this whole program of Hilbert's sixth problem. So Hilbert's sixth problem is to derive the macroscopic laws of sort of physics from microscopic dynamics. And at least for this model, this holy grail would establish the heat equation for the Lorentz gas. But we do not claim to have solved this holy grail. So let me warn you there at the start. Let me go a little bit into the history. So first, the history of the periodic Lorentz gas. In a sense, the periodic Lorentz gas is slightly easier. And this is because you can fold over the domain, and you're now in the world of dispersive billiards. So there is a huge literature of work going back to Sinai and Bonimovich in the 80s. And this led to various results establishing the kind of invariance principles that we're looking for. There are still some open questions in certain dimensions, but let me just say that the periodic in the macroscopic sense is relatively well understood. I know this is the random picture, but let's ignore this. I want to introduce a particularly interesting regime, which is the so-called Boltzmann-Grad limit. So this is very common in statistical mechanics to take this limit where the radius of the potential goes to 0, but we increase the density, and we increase it proportional to r to the d minus 1. And with this, we have still order 1 time between the collisions. So if you choose the constant correctly, then the mean free flight time will just be 1. Now, what's nice about this is that the collisions are very well separated, at least compared to the size of the scatterers. And this means one expects to have more Markovian behavior, at least intuitively. So the last thing I'll say about the periodic Lorentz gas is what happens in this Boltzmann-Grad limit. So in this case, the periodic Lorentz gas can be understood in terms of homogeneous dynamics. And at least in 2011, Markloff and Strombergson were able to calculate this Boltzmann-Grad limit for the periodic Lorentz gas. And they were able to show that it converges to a non-Markovian flight process, which satisfies a sort of transport equation. And then Balint and Markloff in 2015, they were then able to take this non-Markovian flight process, and they were able to prove a super diffusive central limit theorem. So it's super diffusive because one could imagine if the size of the scatterers is quite small, you would get these kind of infinite channels appearing in the domain. So one sees the super diffusive behavior in the limit, in this Boltzmann-Grad limit. Now, and so they prove an invariance principle in this limit. Let me emphasize what's happening here. First, Markloff and Strombergson are applying the Boltzmann-Grad limit, the kinetic limit. And then Markloff and Toth are applying the diffusive scaling. So their theorem applies only to this flight process, to this limiting flight process, right? Unlike the Holy Grail, which just says apply the diffusive scaling. Okay. Now, in today's talk, I'm more concerned with the random Lorentz gas. And let me first give you the literature in the Boltzmann-Grad scaling. So for the random Lorentz gas, we know almost nothing for fixed scattering radius. We have to work in this Boltzmann-Grad limit. So this will be a given throughout my talk, at least. So in the random Lorentz gas, in the Boltzmann-Grad limit, Gallavotti was able to show that the Lorentz gas satisfies a Boltzmann equation in the Boltzmann-Grad limit, meaning that the Lorentz gas behaves like a Markovian flight process in this limit, as long as you fix the time, some finite length time, and then you apply this limit, you'll end up with a Markovian trajectory. This was then generalized by Spahn. And let me emphasize that this is in the annealed case. So they are averaging over the scattering set as well as the velocities of the particle. Boldrigini, Bunimovic, Sinai were able to again show the same convergence to a Markovian flight process in the quenched limit. So here they fix almost every environment, and then they average over the velocities, and they prove the same limit. So again here, let me emphasize that this is for finitely many collisions. The random Lorentz gas behaves like something Markovian. Now, one could then apply the diffusive scaling to this limit process, and it's a simple application of Donsker's invariance principle that one achieves this invariance principle for this Markovian flight process. But again, we are applying first the kinetic and then the diffusive limits. Okay. Let me present our main theorem. So, okay, formally, our point process is going to be a Poisson point process. And we have this x of t is the associated random Lorentz gas. And we fix a macroscopic time, which is no greater than r to the minus 2 with a log factor. We assume the Boltzmann-Grad scaling. And now we're able to apply we're able to prove an invariance principle. But notice what I said before, that we have mean free flight time of order 1. So the number of collisions is extending all the way to r to the minus 2 as r goes to 0. So in a sense, this is an intermediate scaling limit where we're simultaneously applying the kinetic and the diffusive scaling. So our trajectories get longer and longer as we apply this Boltzmann-Grad scaling. Yeah, that's what I've just said. Are we all happy with the main theorem? Okay. We have recently, or not so recently in one case, been able to extend this theorem. So let me just highlight a couple extensions. So in 2 dimensions, we can generalize the setup by adding a magnetic field perpendicular to the plane, in which case your particle moves in these circular orbits with some radius, which you can just set to equal to 1. And this is also a very well-studied model. In the 90s, Bobby Levitt and collaborators were able to derive a transport equation for this magnetic Lorentz gas, which was also studied by Kuzmani and Spahn. This was recently derived more rigorously by Noto, Safirio, and Simonella, again in the kinetic limit. So this is like this previous work I showed you on the random Lorentz gas. So in the kinetic limit, they get some sort of non-Markovian flight process that comes as the limit. And together, this is in preparation. Balint and I were able to prove, again, a kind of intermediate scaling limit between the diffusive and the kinetic limits. So we are now taking times of order r to the minus 1. Again, we apply this Boltzmann-Grad scaling, and we get convergence of the Lorentz process to a Wiener process. One has to avoid these trajectories where the particle hits nothing, which is why this is a slightly different process. Note that the time scale here is r to the minus 1, whereas before it was r to the minus 2 in 3 dimensions. This is essentially due to the recurrence and transience of the random walk in 2 dimensions versus 3. Has nothing to do with the magnetic field. Okay. And the last extension that I'll say is to this random wind tree model. So in 1912, the Paul and Tatiana Ehrenfest, they introduced this model, which is like the Lorentz gas, except we replace the spheres with cubes. So you see this kind of more jagged behavior. And now the velocity will be restricted to 4 or 8 directions. In 2 dimensions, this is a really hot topic over the last 20 years, because we replace, whereas before with the Lorentz gas, one had the billiard table. Here, one arrives at a translation surface. And so there's a lot of very advanced ergodic theory work that goes into this stuff. And that's as much as I should say before entering into unknown territory. But the headline is that no invariance principle has been proved, and I don't think an invariance principle really holds in this case. There are kind of interesting directions where one gets strange diffusive behavior. In the random case, one can use this old result of Gallavotti to say that in the Boltzmann-Grad limit, so in this kinetic limit, we again get this Boltzmann equation. So in the kinetic limit, we arrive at Markovian behavior. So with Balint, and this is now a few years old, we were able to prove the following, again, intermediate scaling limit theorem for the wind tree model as well. So here we work in 3 dimensions. And again, we're in the random case. We have this Poisson point process. And we fix an initial velocity, fix our macroscopic time, fix our Boltzmann-Grad scaling, and we get convergence to a Wiener process. Now, the Wiener process is biased in the direction of the velocity, right? If you have a very vertical velocity, then you expect the particle to move further in the vertical direction than in the horizontal direction. This is the only difference. And note that we get a slight improvement on the time scale. We can avoid some log factors, and this is because the geometry of collisions is much simpler. Okay. But that's pretty much all I'm going to say about the wind tree and the magnetic Lorentz gas. So let me move on to an idea or a sketch of the proof for the random Lorentz gas. So the key insight is to reconstruct the Lorentz gas as an exploration process. So rather than think about fixing an environment and exploring the environment, we think of the particle constructing the environment as it goes along. So in order to explain this, let me introduce this Markovian flight process. For this, we fix some random data, which is just exponential flight times and uniformly distributed velocities. And we consider what we call the Markovian process. There's a discrete process, which flies for time psi1 in direction u1, and then it flies for time psi2 in direction u2, etc., etc. And there's an associated continuous process. So here's the picture. We start at the origin. We fly in direction psi1 for time u1. Sorry, direction u1 for time psi1, direction u2 for time psi2, etc., etc. And it just keeps going in a completely Markovian behavior. One can apply Donskoy's invariance principle, and we get the invariance principle for this Markovian flight process. So this is well-known kind of classical invariance principle. Now, let me construct the associated Lorentz gas as an exploration process. So this will be coupled to the Markovian process. So again, we select our random data, and then we'll be coupling these two processes together, constructing them from the same data. The first path segment is very simple. The Lorentz gas, this is x of t, and the Markovian y of t, they begin parallel and they travel for the same amount of time. Now afterwards, the Lorentz gas adopts the same velocity as Markovian and travels in the same direction. But for the Lorentz gas, it places a scatterer where the scatterer should be in order to have this trajectory. And then it continues doing this ad infinitum. Okay. Now there's two things which can go wrong in this setup. And we call these things mismatches. So the first mismatch is what we call a recollision. So notice the Markovian does its thing. It travels here, 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 here. There's no problem. The Lorentz gas tries to replicate the trajectory. So it travels in the same directions. But here, the Lorentz gas can no longer obey the same trajectory as the Markovian because it's blocked by a previously placed scatterer. And the Lorentz gas is a physical process, so it has to obey this scattering. Now, the next time the Poisson clock rings, the next time the Markovian process makes a jump, the Lorentz gas will try and make the same jump in order to recouple with the Markovian. Right? So now the processes have been translated. They are no longer in the same position in space, but they again have their parallel trajectories. So this is one kind of mismatch. The second type of mismatch we call shadowed collisions, although I've heard other people call them interference collisions. And it's the time reversal of a recollision. So let's see what's happening. The Markovian again does its thing. It makes this trajectory. And the Lorentz tries to make the same trajectory. But if the Lorentz were to obey this next collision, it would block its previously explored path. This is illegal. This is not physical. So instead, the Lorentz gas will simply ignore the shadowed collision. And then the next time the Poisson clock rings, it recouples with the Markovian. So we have these two kinds of mismatches which create decoupling, and afterwards we attempt to recouple the processes. And it turns out that with this exploration process, one recovers the Lorentz gas. So now we can study the Lorentz gas by studying this Markovian process. And the first lemma, which I want to highlight, is the following. Whoops. So this is a lemma about the Markovian process. And we ask, what's the probability that the Markovian process returns to a neighborhood of a collision? And the neighborhood will be proportional to the radius. And we're going to separate this probability depending on how many intermediate collisions there are. So here I give you, these are two recollisions. On the left-hand side, when k equals 1, the Markovian process y sees a scatterer, sees another scatterer, and then returns back to the original scatterer. And here, when k equals 2, the Markovian sees a scatterer, it sees two more scatterers, and then it returns back. So these are what we call k-fold recollisions. And the lemma here, which is a purely probabilistic lemma, it says that when k is less than d minus 1, this is proportional to r to the k. When k equals d minus 1, we get r to the d minus 1. And when k is larger than d minus 1, we get r to the d minus 1 again. This is where you can see the recurrence or transience of the random walk. In 2 dimensions, all of these are the same. All of these are r to the 1. And so we see these, what we call indirect. So this indirect means k is larger than 1. we see these indirect recollisions happening at the same frequency as the direct recollisions. But in higher dimensions, we only see the direct recollisions up till time t to the minus 2. And then after time t to the minus 2, we start to see more complex recollisions, indirect recollisions. This will be very important. Here I give you an example of a direct or an indirect shadowing. So again, direct means that there's only really two scatterers involved. Indirect means that there are more than two scatterers involved in the shadowing event now. And again, the same theorem holds. I should have said k-fold mismatch here. The same theorem holds for shadowing events. So to put this in words, when d equals 3, up till time r to the minus 2, we only see direct mismatches. And the probability of a given collision resulting in a direct mismatch is r. So again, I want to emphasize, I haven't said anything about the Lorentz gas. I've only said something about the Markovian process at this stage. You can prove this using kind of Green's functions or various probabilistic techniques. And again, this is not true in dimension d equals 2. This is the main obstacle in dimension d equal 2. Now note that this allows us to prove our statement for times up to r to the minus 1. Because up to time r to the minus 1, we don't even see any direct mismatches, or r to the minus 1 plus epsilon, let's say. So we call this the naive timescale, but please take note that this is not a trivial timescale. This is still infinitely many collisions, but it's naive in the sense that we see Markovian behavior up to this timescale. So we can already prove our main invariance principle up to time r to the minus 1. But how do we go beyond? That's the question now. So to move beyond these timescales, we have the following lemma, which I state more in words than formally. And it says that with high probability, after a direct mismatch, the time spent before the recoupling is of order 1. Now, one could imagine a sort of trap occurring. In other words, that you have maybe 3 or 4 scatterers closely arranged, and the particle enters into this trap, and it can never really escape, in which case recoupling would be very difficult. Now, what this lemma is saying is with high probability, recoupling will happen on a finite timescale. This was actually kind of the main meat of the proof and requires kind of both geometric and probabilistic analysis of these recollisions, which I might say more about in a moment. Okay, now let me give you a sketch of the proof, and then I'll explain a bit more some of the details. Now that we have these two lemmas. So I first defined the velocity processes, and we want to understand the separation between the Lorentz process, the true mechanical process, and the associated Markovian process. And we are allowed to divide by t to the minus a half thanks to the diffusive scaling. This separation will just be the integral of the difference of velocities. Now we apply the triangle inequality. Oops. And bring the absolute values inside. Now we're going to upper bound this, the difference of velocities by the probability of a mismatch times the number of collisions times the time spent before recoupling, right? The time spent before the trajectories are now parallel again. And then we still have our t to the minus a half. We have the probability of a mismatch is r. The total number of collisions is capital T. The time spent in recoupling is of order 1, and we have the diffusive scaling. So if you plug in all of these things, we get something that goes to 0. Now, since the y process satisfies an invariance principle, the x process now also satisfies an invariance principle. Now, the rest of the proof is just formalizing these steps. Let me first highlight one aspect of the proof that I haven't mentioned so far, which is what's going to happen is we're going to have these long periods of Markovian behavior of time r to the minus 1. After that, there will be a mismatch. The particle will spend time in this mismatch, and then recoupling will occur. This all happens on a time scale of order 1. Now, after that, we're going to glue a second Markovian piece to this to the end of this piece. We call these legs of the trajectory rather than path segments. And this second leg will also have a recollision or a mismatch at the end. And so the point is to concatenate these Markovian legs to build up the new process. In fact, in the proof, we have to introduce a third, I think we call it a forgetful process. So it's not Markovian, but it's kind of forgetful process built from these different legs. So we concatenate these Markovian legs. We need to control the probability of a mismatch within each leg. That's kind of what we've already done. And then we need to control for the geometry of the mismatches. Again, that's the second lemma I showed you. And then we need to control for the probability of the mismatches between the separate legs. And this is a sort of Green's function argument, which is relatively standard techniques, but still needs to be done, of course. Let me now let me see how much. Okay, I have 15 minutes. Let me now highlight a second aspect of the proof, and this is the geometric lemma, because this is really one of the novelties of this proof. And the question is, how long does one spend in a recollision? I'm only going to talk about recollisions, not shattering events, but the same applies. So first, we parameterize the space of double collisions. There is a rotation invariant, so let's assume the particle enters with velocity e1. And then the double collision is parameterized by the second velocity, the space between the collisions, and the third velocity. Yeah, and that gives you, then you can reconstruct the double collision. So we have this overall space of double collisions. We can associate measures to these spaces, and we're going to want to scale the x by an exponential because of our exponential flight times. And then the velocities get uniform distributions on them. And now we can apply our Boltzmann grad scaling by scaling the x by r to the minus 1. So now we're keeping the scatterers the same size, but we're somehow scaling the distance between them. It's just a bit easier that way. Now, inside of this space D, these are the space of double collisions. We can isolate the subspace of recollisions. And it looks like this. I mean, this is the position of the scatterer. This is the center of this scatterer here, the top right scatterer. And this line is this final line out here. So a recollision happens if this line gets within an R neighborhood of this center over here. That's all this is saying. And we can scale the R out by applying this scaling, this R scaling that I introduced on the previous slide. And the two things we want to understand are the trapping time, which we call beta R, and the escape velocity WR. And we want to show that the probability that the trapping time is bigger than R is proportional to R. So it goes away in the limit. And we also want to show that the escape velocity is not too similar to the incoming velocity. Right? If I had it would be quite bad if I had a recollision and then my particle had the velocity E minus E1, because then it would just backtrack over its own trajectory. So these are the two things we need to control: the time spent in this recollision and the velocity, the exiting velocity. This is U plus V out here. I don't really have time to go into the proof, but the key idea is we define a plane, which is kind of hard to draw, but we think about a plane which connects the two centers of the spheres and the first collision point. And the point, the way we prove this lemma is to notice that the velocity perpendicular to this plane can only increase because the spheres are convex. And so this velocity, we can control the probability of this incoming velocity and its projection perpendicular to the plane. And this will give us a lower bound on, or an upper bound on the trapping time. And the same for this backtracking, this escape velocity. So that's kind of the key idea for this geometric lemma, which allows us to control the probability, these two probabilities here of getting stuck in a mismatch or the backtracking effects. Okay. Now, I have 10 minutes left, so 5 or 10 minutes left. Let me explain the key ideas for the wind tree model and the magnetic Lorentz gas model. So for the wind tree model, the geometry of the mismatches is much simpler, right? Because if you consider a recollision, this can only happen if you have two squares or two cubes quite close to each other, and the particle just bounces back and forth between the cubes. In particular, for the Lorentz gas, these recollisions will often happen with very small angles, and the shadowing will also happen with very small angles. And this is what gives you these log factors in the time that we can prove our theorem, is through these sort of small angle collisions. But for the wind tree, we don't have these small angles because the velocity set is discrete. And so that's why we can improve slightly the time scale for the wind tree model. The complication, however, is that the flight process is no longer IID, because not all velocities are accessible from each other. So for example, in 2 dimensions, if I'm traveling up and to the right, um, after a collision, my velocity has to be up and to the left or down and to the right. I can never completely reverse my velocity. So we have a true Markov process. But this isn't really a big problem. What we do is we split the process into excursions, meaning that we simply wait until we have the same velocities, right? Wait until we return to the original velocity, and this gives us a little excursion, and these form the legs of a sort of slightly larger IID Markovian process. So after this splitting, we can apply the same kind of techniques that we did in the Lorentz process. And so we end up with the same sort of theorem. Now, lastly, I want to talk about the magnetic Lorentz gas. So this is some ongoing work which should be out in the next few weeks. And one of the main difficulties here, and this is why there was all this work on the kinetic limit of the magnetic Lorentz gas, one of the main difficulties is what we call self-recollision. So if you notice here, the particle is doing these circular trajectories, and it can re-encounter the same scatterer without seeing another scatterer. So here there is a self-recollision. Yeah, there's a self-recollision. And what this means is that the Markovian process now depends on the radius of the scatterer, right? Even if we forget about all the other scatterers and follow this trajectory, we're going to have these kinds of self-recollisions popping up. So this makes the recurrence equations for this magnetic Lorentz gas much more complicated in this limit. And the second difficulty is that in 2 dimensions, the collision kernel is not uniform. So the magnetic Lorentz gas, right, it's sort of trivial in 3 dimensions because you get these sort of spiral trajectories. So it will just look like a normal Lorentz gas. But in 2 dimensions, the collision kernel is no longer uniform. And so again, you don't have a fully Markovian process. So it's kind of analogous to the wind tree model, where the collision kernel was discrete. So again, we need to do some splitting up, and this time we have to use some slightly more advanced probabilistic tricks, namely Dublin's condition, Dublin's inequality, to split up our path into independent IID pieces. Yeah, and then we have this complicated geometry, which is determining our recurrence equations. So the magnetic Lorentz gas is quite a lot more work, but the kind of surprising conclusion is that we again just see a Wiener process popping out at the end, at least in this Boltzmann grad scaling. And again, now our times are of order r to the -1. And this is not anything to do with the magnetic field. This has to do with the fact that we don't want to see complicated mismatches. We don't know how to handle indirect mismatches because the geometry gets too crazy. Okay, so I think that's more or less the end of my time. So I'm quite happy to take questions if there are any, and if my audience is still there.
So maybe let's first thank you for a really nice talk, Chris. So indeed, if there are any questions, feel free to unmute yourself or write them in the chat. Or maybe let me actually start with a question for you. So it seems to me that in principle, this argument should work whenever you put any convex shape, right? So you don't necessarily have like a sphere or somehow when you look at the wind tree model, is there any obstacle that somehow if you go like say for like any like
I
convex
think
shape?
for a convex shape, you shouldn't have any obstacle.
Okay.
One might have the problem that the collision kernel is no longer uniform. And so you might have to do some extra breaking up into IID pieces. But as long as you have convex, it shouldn't be a problem. If the scatterers are no longer convex, then this geometric argument,
Yeah.
this geometric argument here would break down. Because you could imagine being trapped in a sort of worse situation if you lose convexity. But I think anything convex would apply. Yeah. So your
Thanks.
potatoes would be fine.
Very good. Okay. So any questions from the audience? If not, maybe a brief second one. So you mentioned at the very beginning also the periodic case. Could you think of somehow something like in between, like a periodic model where you just have some impurities, so just some uh, like points where somehow your periodicity is perturbed, and you could still try to ask the same questions?
Yeah. So I think you should look at the work of Marco Lenci. He's done quite a bit of work on kind of introducing randomness into the periodic setting. So I think he has looked at a sort of sparser periodic setting where you remove certain scatterers, with some Bernoulli probability. And he's looked at a few other varieties of introducing randomness. I'm not sure one can say anything that interesting, or one has said anything that interesting in that setting. I think as long the sort of sparse setting where he removes certain scatterers, he needs he needs it to be dense enough that he doesn't notice the removal of the scatterers. So it's yes, these kind of intermediate models exist and people have studied them. But they tend to work either in the very periodic setting, where they look very periodic. I see there's a question by Andrzej.
Thanks for a nice talk. I just wondered during the talk you mentioned the issue of dimensions. Is there anything you mentioned this line, some kind of a phase transition in the middle of your talk, but is there any issue in any special higher dimension, say than 2? Are there any differences? Are there any possible dimensional issues here? Thanks.
Yeah, so it's a very good question. In dimension 2, all recollisions are equally likely. In dimension 3, let's ignore this log factor. In dimension 3, direct recollisions happen on timescale r to the -1. Indirect recollisions happen on larger timescales, any t to the -2. If you were to move to dimension 4, for example, you would see the direct recollisions at time t to the -1. Maybe I can annotate. So you have t to the -1 for the direct, t to the -2 2 for the k equals 2. And then all of the indirect higher dimensions, higher fold recollisions would happen on t to the minus 3. And so you get this separation between the different k's, which would happen in higher dimensions. So I think if I wanted to, if we cared a bit more about higher dimensions, one thing which would be interesting would be to see if you could extend our theorem in dimension 4 to t to the minus 3. Because then the only extra geometry that one needs to handle is k equals 2 collisions. And maybe there's some hope in that case to get a handle on the geometry. The real problem is once you get to this stage, when k is bigger than t minus 1, you have indirect recollisions, you have indirect recollisions inside of other recollisions, and all of these different factors start to come into play, and we just don't have a handle on the geometry of that. So this phase transition does get larger in higher dimensions, or does get further away in higher dimensions. So there's some hope to handle kind of slightly more complicated recollisions without going all the way up to this dimension, up to these k. Yeah.
Okay. Thank you. Thanks.
So are there any more questions? Okay, so doesn't seem to be the case. So thanks again, Chris, for the very nice talk. And let's maybe do a 2-minute short break before continuing with part 2 with Balint. So Balint, you mind? Oh, you're still muted, Balint.
Yeah, now you can hear me, and I will share my screen, not my screen, I hope to. Let me see. Yes. And give me a second. I want to see the faces as well, and that's what makes my yes, now
Yeah, now it works.
it will work. It will work. I know how to do it. Oh no, it hides my slide. Why does it hide my slide? Give me a second. I still have a little time, yeah?
Yes.
To arrange my screen, because I have a way to do it that I have my stuff on one of the screens. Yes, and I have people on the other screen. And do you see my shared slide now?
Yeah, looks very good. Maybe you can just try to go one forward or one backwards, backward maybe
Yes.
to see.
Control L first, and how is it now?
That looks very good.
Dominic, does it move?
Yes.
Good. Okay, so then I'm about ready to start. Shall we wait till the hour, or?
Oh, I think we can actually start now. So let me maybe just say briefly, thanks a lot for giving like the second talk. So we have Balint Toth speaking about, again, Lorentz gases, like the second part. So Balint, here you go.
Thank you, and thank you very much for organizing this seminar. And it's a pleasure to speak to people geographically so much spread out that I have to say good morning, good afternoon, good evening, and good night to some of you, I hope. Good. So this is my title now: Invariance to Words, an invariance principle for the random Lorentz gas. under the weak coupling limit beyond the kinetic time scale, and I will explain all these terms now. So it will be, of course, in the spirit of our previous work about which Chris gave his presentation, but it's another kind of kinetic limit. Now, for those of you who have some minimal background in physics, you know, or not only in physics, let's go to probability. In probability theory, when you do first course in probability, you know, you learn about two basic limit theorems. One is the Poisson approximation of the Bernoulli. Okay, take the Bernoulli. You have the Poisson approximation of the Bernoulli at one hand, and you have the central limit, the Gaussian of sum of Bernoullis, and you have the Gaussian approximation of sum of Bernoullis. These are in two different scaling regimes. So if you add rare Bernoullis, rarefied appropriately and the long sum, you get the Poisson approximation, and that's what we have seen in Christoph's talk just before, that we are in a physical setting, that we have these scatterings among fixed scatterers, and if the scatterers are arranged in such a way, and this is the Boltzmann-Grad limit, that you see rarely one, but each single one has a big effect, that's the Boltzmann-Grad limit. That there is another kind of kinetic limit, and this is the weak coupling limit I'm going to speak about, when you don't rarefy your scattering events, but you make each single scattering scaled down to have a small impact, each one. And that would be, in the probabilistic context, that would be the Gaussian approximation. So my talk will be about a very similar problem, but in a different scaling regime. And both are physically relevant. So Boltzmann-Grad came up, as Chris very clearly explained, in the early 20th century with the work of the Lorentz gas. I mean, this type of hardcore Lorentz gas in the work of Hendrik Lorentz and then Paul and Tatjana Ehrenfest. These were more than 100 years ago. And the weak coupling limit I will speak about is somewhat later, because in the context of plasma physics, it came up. We will not hear about plasma physics, by the way, in Landau's work. Okay, so let's see what I'm going to speak about. Tell me if there is any problem with the slides. If you see my slides, then it's okay. Yeah. Do you see my slides, Dominic? Yes. So my ingredients, the ingredients of the model I'm speaking about, are what? A smooth potential. By smooth, I mean at least twice continuously differentiable. A potential which is compactly supported and spherically symmetric. And C2, of course, I can choose some numbers here. I will choose that the radius of interaction is 1. Spherically symmetric, you see it there. And let me choose the supremum, the maximum of the potential be 1. I'm free to choose some constants. And I also need a Poisson point process in RD. I will denote it by omega epsilon. Omega epsilon is a Poisson point process in RD of intensity epsilon to the minus d. That means that in volume of 1 cubic meter, you have epsilon to the minus 3 points, right? So this will be my, for some convenience, this is not essential at all, but I will assume, so Poisson point process, but with the restriction that in the epsilon neighborhood of the origin, I don't have points. So it's outside an epsilon radius, a sphere of radius epsilon. You will see why that's not an essential thing, but it makes my life a bit easier. Now I create a potential and the force field in RD in such a way that the potential, which I denote by capital phi, will be the sum of these individual potentials, each one centered at a point of my Poisson point process. So at each single point of the Poisson point process, I have a soft potential, right? I have a soft potential, but scaled down to interact within radius epsilon. So it's the same function, but scaled down to act within radius epsilon, right? And also the intensity of the potential is multiplied by an epsilon to the 1/2. As opposed to in Chris's setting, this would be hardcore potentials centered at each point of my scatter of my Poisson point process. So what is the difference? What is the difference between what Chris did and what I do? Chris had he used other symbols, but it was epsilon to the minus the huge density, and radii of the scatterers was smaller than just linearly shrunk, a little bit smaller. I take the radii of interaction exactly as everything would be just scaled down linearly by epsilon, but I multiply the intensity of the smooth or the soft potential by square root of epsilon. Chris couldn't do it because in Chris's case, it was an infinite potential. Multiplied by epsilon, you don't get anything, right? So this is the difference. And the force field is the gradient of the potential field. I can speak now about gradient because it's a smooth object, what I speak about. By the way, this sum is well defined for at any point x. Within radius epsilon of any point x, you will have finitely many points. So this sum is, for any fixed x, this sum is finite. It's well defined. When you take the gradient, you get another epsilon to the minus 1 out from inside, so you get all this multiplied with epsilon to the minus 1/2 as the sum of the force fields created by each of the scatterers. Good. So let's summarize. The potential typically is of order square root of epsilon. The force field is typically of order 1 over square root of epsilon. Good. And what is the Lorentz process? The Lorentz process is the mechanical process, as you learned in Newtonian mechanics, moving in this force field. So I have a particle, its velocity is denoted by v, its position is denoted by x. Both are in Rd, of course. X dot, that means time derivative of displacement, is the velocity, and v dot, according to Newton's law, is f. And I'm afraid that here 1/2 is missing because I take my particle of mass 2 for some reason. So 1/2 is missing from it. Good. And it starts from the origin, and the initial velocity is unit velocity pointing in some direction. Good. The total mechanical energy, as you learned in classical dynamics, the total mechanical energy consists of kinetic energy and potential energy. And as I told you, I took the mass of the particle 2 in order not to carry the 1/2 all the way. Yes? So it's v squared plus phi at the current position. That's kinetic plus potential energy. This is 1 for all times. This is just conservation of energy, right? And if I started with no particle within range of interaction, no scatterer within range of interaction, and velocity 1, then I started with kinetic energy 1, potential energy 0, total mechanical energy 1. This is conserved all along the time, right? And again, we see this holy grail here. One would like to understand, and this is an absolutely great problem in mathematics, in mathematical physics, and in probability, I would say. Look at the trajectory of this particle and try to prove a central limit theorem. The dynamics, as in Chris's case, is fully deterministic. That's the point. Randomness comes only from the initial condition, the initial displacement of the fixed scatterers, and possibly the initial random orientation of the initial velocity of the particle. Otherwise, the dynamic is fully deterministic. Nevertheless, the trajectory is a random trajectory because the dynamics is deterministic, but it takes up the randomness from all over. So question is whether, and of course, we expect that such a thing holds. You will see a little bit of warning on the next slide. I'm sorry, I mixed typed and handwritten slides. I hope, can you see the handwritten slides reasonably well? Good. And this was already a problem I mean, not a problem, but in Chris's case, you could have your particle trapped. That's a percolation problem. So there is positive probability that the origin is surrounded by scatterers in such a way that the particle cannot escape at all. But this event is of positive probability, but less than 1 Okay, that's a percolation argument to see in Chris's case that if the density is not too high, then you have positive probability to escape to infinity. That's a Bernoulli percolation problem. And in my case, again, it is the case that if I keep now, in my case, the density and the radius to the power d is constant, doesn't go to 0. Nevertheless, if I take the maximum of the interaction potential sufficiently small, then with positive probability, there is a route out to infinity such that along that route, the maximum potential barrier is less than 1, so the particle can escape to the infinity in principle. That's an elementary thing. This is not important, but better we clarify that we have to make an assumption here that the particle is not trapped forever in a compact domain. But in my limit, as in Chris's limit, the corresponding rho times r to the d went to 0, and therefore, with high probability, overwhelming probability, there was way out to infinity. In my case, as I multiply with square root of epsilon the interaction potential, with overwhelming probability, the particle will be able to go, right? So let me go back one page. So assuming that the particle is not trapped, so that there is no trivial obstruction to the central limit theorem, but the assumption is of positive probability, the condition is of positive probability, prove the central limit theorem. This is way beyond our possibilities, and probably it will not be proved in our lifetime. But this is indeed, keep in mind that this is something very important. Okay, now what is the weak coupling limit? As opposed, so this is different of what Chris did. As opposed to, so now I take the radii of the particle, of the interaction radius of each single scatterer is epsilon. The density of scatterers is epsilon to the minus d, is just like as if you had order 1 object scaled down linearly by epsilon, right? But you also multiply by a square root of epsilon the interaction strength. So that's why we call it weak coupling limit, right? Scale down linearly everything and multiply the strength of the interaction, the square root of epsilon. And this is just repeated from a previous slide, that the potential, typically everywhere, the potential will be of order square root of epsilon. And the force field acting on the particle at the typical point will be of order 1 over square root of epsilon. And we solve this equation. So it's just a repeat of what I did before. Now let's try to guess what kind of limit to expect. Let's try to guess together what kind of limit is expected. First of all, I have the conservation of energy. So this is kinetic energy, this is potential energy of my particle. The potential energy is of order square root of epsilon, because essentially everywhere the potential will be of order square root of epsilon. I started with full mechanical energy equal 1. This is very small, say 0. So the kinetic energy will be 1 in the limit when epsilon goes to 0. So my particle in the limit travels with speed 1 in random directions and changes directions, but the speed is 1. Keep in mind. Now in time dt, the particle, the traveling particle, will encounter epsilon to the minus 1 times dt scatterers, because the scatterers are packed. So it's just the whole picture is scaled down, is zoomed out by a linear factor epsilon. As the particle travels with speed 1, it will meet epsilon to the minus 1 dt scatterers in dt time, right? On the other hand, I claim that each single scatterer will have an impact of order square root of epsilon on the velocity. Let's see why. This is the picture which explains why. This is one scatterer, linear size epsilon. The particle travels on the green trajectory with speed 1. That means it spends typically time of order epsilon inside, but the force is of order epsilon to the -1/2. So when traveling through one single isolated scatterer, the particle collects that much change in the velocity. This is Newton, right? So you have the force acting is of order 1/√of epsilon. It travels time epsilon. Altogether, the impact will be √√ of epsilon. So let's put these things together, all these three things. Travels with speed epsilon. In time dt, it collects that many kicks of that size, and these are random kicks. Of course, this is to be made clear what I mean. So it's a central limit effect. You see, a central limit effect. Many kicks of size 1/√√ of that many. But on the other hand, it stays absolute value 1. What is this object? What is this limiting object? This limiting object will be a Brownian motion or Wiener process on the unit sphere. I speak of the velocity. The velocity of the traveling particle in the limit, in the weak coupling limit, is expected to be a Markov process, a diffusion process on the unit sphere, which has infinitesimal generator, the Laplace-Beltrami operator. So that's Wiener Brownian motion on the unit sphere. This is the velocity process. And the position, the displacement will be, of course, the integral of the velocity. So what we expect, this is the counterpart of that flight process which Chris explained in the weak coupling, in the Boltzmann graph. In the Boltzmann graph, the limiting process was a Markov process on the unit sphere, but it was a pure jump process. You had the unit sphere, and you jumped from point to point according to a transition kernel. So that was the Poisson approximation, let's say. And now I speak about the Gaussian approximation. In this limiting procedure, the limit in the limit you expect the Wiener process, a Brownian for the velocity of Brownian motion on the unit sphere, and the position be its integral. Now, this was not that easy to guess as it was in the Boltzmann graph case. Even to guess it was, I think, harder, and even harder to prove. Nevertheless, Harry Kasten and George Papanikolaou proved this theorem back in 1980, about the same time as Galavotti and the papers quoted by and Sinai and those papers quoted by Chris, right? And I'm happy to mention Kasten's name here because most of you, I mean, today's probabilists link Harry Kasten with percolation and with discrete probability and discrete objects and so on. Mind, Harry Kasten did this type of things as well. Good. Okay, on the next slide, I simply collected this statement. So what I call the spherical Langevin process is a probabilistic object. The spherical Langevin process is exactly what I spoke about. Vt is a Brownian motion on Sd -1, and xt is its integral. And this is what I will call the spherical Langevin process. And what Kasten and Papanikolaou proved back in 1980 is that it's a wonderful paper, by the way. It's very technical, but a wonderful paper. In dimension 3 and more, take any fixed time, t is fixed, capital T, and look at the process. This is when you see the epsilon, this is the physical process, the mechanical process moving among the scatterers. Let epsilon go to 0, but this is the weak coupling limit now, not the Boltzmann graph, the weak coupling limit. This process will converge to the spherical Langevin. A constant comes into the story, which depends, and essentially it's explicitly computable from the interaction potential. So this is Kasten and Papanikolaou, and this is the counterpart of Galavotti-Spohn in Chris's talk. Let me make some remarks on Kasten and Papanikolaou. First of all, Kasten and Papanikolaou prove more. They consider much more general cases, actually much more general potential fields, not only potential fields coming from Poissonian point process and so on. Actually, they consider force fields which are not gradients of a potential. So it's a much more general setting, but for our purpose and for my physical purpose, this is the most relevant concrete example of Castellan-Papanicolaou. Again, as in Chris's talk, recall that Chris said at the point that, look, Galavotti and Spohn did the kinetic limit. As a second limit, take diffusive limit of what you get out from the kinetic limit, you get the Brownian motion. And this can be done here as well. Because in the kinetic limit, I get this process, what I call the spherical Langevin. Here, xt is the integral of Vs, but Vs is a very well-behaved Markov process. It's a Brownian motion on a compact manifold with a gap in its spectrum, so you can apply your favorite central limit theorem or invariance principle. Mine is a Dublin type of proof, but you can apply Kipnis-Svaradan or other things, and you get it out. So as a second limit, again, you get the Wiener process. And the question is, of course, the same. Can you do better than this? Can you do better than this? By this, I mean what Chris meant, that rather than prove kinetic limit for finite time horizons, then in a second limit, prove the kinetic, prove the two at one stroke, increasing the time horizon to infinity at the same time when you take the kinetic limit. It's much more difficult because if you do the two steps, then in the first step, you sweep out all memory from the system. And you prove in the second step, you prove the central limit theorem from a memory-less system. And in this mixed limit we are doing, in the interpolating limit, we do the hard stuff. Some harder stuff. We take into account recollisions and all. Good. So try to interpolate between the two steps limit, which is what I just explained, and the Holy Grail, which is just the bare, what I call the bare diffusive limit. So without taking kinetic, without scaling down the epsilon, and try to do something between. And actually, in this context, there is a result in this spirit. There was a result in this spirit before we did our work with Chris on the Boltzmann. In the Boltzmann context, there was none, but in this context, there was. And there is this paper by Tomasz Komorowski and Lyonia Rizsik, where they do exactly this type of thing back in 2006. So they say the following: take a time horizon. First of all, we are in dimension 3 and more, as it was before. Take a time horizon which goes to infinity, but not faster than epsilon to the minus kappa, where kappa is a positive number. By the way, this kappa is positive, but very, very small. So the epsilon is slightly smaller than epsilon to the minus kappa, and kappa is 1/300, say. Then, indeed, in the joint limit, the displacement in the joint limit, there is an invariance principle for the displacement in the joint limit. It is joint limit. So that's what Komorowski and Rizsik do. Okay. Now my point is to improve this theorem. So this type of theorem, let me comment on that. Again, Komorowski and Rizsik, as Castellan and Papanicolaou, they do it in more general potential fields. But this is the most interesting example of the potential fields they look at. In this type of theorem, I go back to the theorem. In this type of theorem, the larger the kappa, this kappa corresponds to the d-1 in Chris's term. The larger the kappa, the closer you are to the Holy Grail. If you could prove such a theorem for whatever kappa as large as you wish, then you would be not yet at the Holy Grail, but almost. Anyway, this is my second comment. The third comment is that gamma in the Komorowski-Rizsik work, kappa comes out from some very, very worky and technical partial differential equations, estimates, and so on, which are out of control in the end. So they don't even say how small it is, but certainly it is in the order of 1/100. So it's small. And what I want to add here, there is a very famous work about the same time, published a bit later, but done at the same time as Komorowski and Rizsik. This papers, actually it's more than one paper by Laszlo Erdős, Zalmhofer, and H.T. Yao, where they do a quantum setting, very, very similar thing in the quantum setting. I would be able to tell you, but it would take another 20 minutes just to explain the terms, so I will not do it. And again, they prove a theorem very similar in spirit. In the Erdős-Zalmhofer-Yao paper, they explicitly say that the kappa they can do is something like 1/370 or something like that. Anyway, that's... Now, what I'm going to report about is I think it's a substantial improvement on Komorowski and Rizsik. I don't say it as a theorem because the paper, it's my shame, because everything is there and it's written down, but not yet fully ironed out. So the paper is not yet available publicly. So therefore, I just say that this is the novelty. Improve it for kappa equals d minus 2. So mind, kappa was something small and not clear how small, and it was done in a very difficult way. I do it explicitly. I get an explicit value of kappa. I get it in 3 dimensions and 3 and more dimensions. I'm not sure I could be able, I think I could be able to do it in 2 dimensions, but I didn't work it out. So let me say, possibly it's doable with log epsilon, some log power. Probably I could go up to that high as in Chris's talk, but I'm not done yet. And so this work is about the point, what Chris called the naive. But the naive is not so naive, by the way. Coupling. So there is more work to be done here. And what's the most important for this audience is that this proof is a probabilistic proof, not a BD proof. Good. Again, okay, now from now on, I have time. I have time. Good. So again, the clue is construct a Markovian object, which is not the limit in the Boltzmann-Grad limit. The Markovian object with which, so it was done what Chris showed you, the Markov process was actually the limiting process what you got in the kinetic limit. Here it is not the case. I have to construct an intermediate Markovian process which helps me prove the thing. So I construct the Lorentz. When I say mechanical Lorentz process, that's the true mechanical physical object I speak about. I denote, and it's exploration. Again, exploration is the key word. So rather than put down, I will show you pictures about it. Rather than, as I told the story, put down the scatterers and let the particle move among the scatterers, I will explore the environment, and the information I have about the environment is just what I've already seen along my trajectory. And then V epsilon t is the velocity of the particle at time t. Eta epsilon t is the explored environment so far. So what I have seen so far, so all those particles, all those scatterers, which I have seen already along my trajectory, are there. So this is a finite set of points seen from the actual position, from the actual position of the walker, which I denote by xt. Xt is just the integral of V epsilon t. V epsilon t moves in the force field created by the already seen scatterers. And occasionally new scatterers appear in my horizon, and from then on, I take them into account again. But there are some restrictions, as there were in Chris's case, namely that new points cannot arise wherever, because I know already something about the environment. And when I go back into the domains where I have been already, then I feel the old guys. Right? I will show a picture about it. And I will also define a Markovized version, a forgetful version of this process, namely velocity, a collection of points, but this will forget about those who are further away. I only keep in mind those who are within range. New ones appear, old ones are left behind, they're forgotten forever. In the original physical process, they were not forgotten, but here they are forgotten. So I make it Markovian. And I try to link, I try to couple these two processes in such a way that I understand the Markovian one. I will tell you how and what it is. And I try to infer information about the physical one from the Markovian. And I hope I can show you a picture, and the picture tells you more than 100 formulas. This is the story I told you at the beginning. Put down the scatterers. These are put down forever there. They stay there put. They have the potential fields around them. And my particle moves around, feels the potential field, and moves as it should move according to Newton's laws. Rather than do that, move as a snake like this. So here, this is the same trajectory, it seems to be, but only those particles are listed here, are shown here, which have been seen already. So when I'm back to somewhere, let's say I explore virgin territory, then when I arrive back here, I already feel I know that there are particles there, so I have to take them into account. Then I again explore virgin territory. Then again I'm back and I have to, no, sorry, not yet back. Then again I'm back and I have to take into account what is there. Of course, it's more complicated than what you see here. And now as I'm here, as I go forward, I explore new things. So this can be formalized. I don't write down formulas. There is an algorithmic way of describing exactly what you have to do, and it's a construction. It's a fair construction. I will tell you what I use in the construction. By the way, I go ahead one page and come back. The probabilistic ingredient of the construction is a cube with a Poisson point process in it. So give me a cube with a Poisson point process, and I give you an algorithm, a very clear algorithm, how to construct this process. And this is the true physical process. Let me emphasize, it's an annealed construction. By annealed, I mean that the motion and the environment are not separated. So the environment is constructed along the trajectory. So it's somehow a joint construction of it, right? And now here is the Markovized version. The Markovized version of the same type of snake. This snake kept in mind, this process kept in mind everything what was in the past. Now I do the same. I travel, but I travel with a sphere. This is magnified there. I travel with this sphere. I have a velocity, which is not bigger than 1, by the way. The speed is between 0 and 1. It's a vector, right? And I have a psi epsilon t, forget about the epsilon is just the index that I'm still before the limit is taken. Right? I have this psi t, which is a collection. So I have the velocity. I have a sphere of radius epsilon traveling with this velocity. The sphere has a front half exposed, the surface of the sphere has an exposed front and a non-exposed back half. Inside the sphere, I have a finite collection of points. This is my state space. So the state space is actually a velocity and a finite collection of points within range epsilon, right? Now, the particle move or the velocity feels the forces created by these points. So you write down a differential, an ordinary Newtonian differential equation, how the motion goes on, but you always move the center, your center of coordinate is in the center of the sphere. You move, but you move according to what these points tell you. Of course, that means that the red points move backwards, right? Because I'm fixed, I'm traveling with the sphere, with the center of the sphere. That means that there is an ordinary differential equation which tells me how the three red points move backward. As I go forward, I see a flow, a Poissonian flow of particles moving in the front, and I can write down formulas for that. That's the same as if this guy moved in totally virgin territory. And when a red point arrives to the boundary, then it's forgotten forever. It's erased from the system. So at the rear half, the points move out and forgotten forever. At the front half, points move in with a Poisson flow corresponding to the speed of my going forward, and otherwise the motion is given by the differential equation, by the Newtonian equations determined by those points which are in there. And as I told you, this is also constructed, both the physical process and the Markovian process are constructed from the same probabilistic ingredient. And I have two algorithms, how to construct them. I hope I told you quite clearly what happens. Yeah, so the difference between the question, yes?
There's a question in the chat.
Yeah, tell me.
So, could the differential equation describing particles within the sphere be partial? So PDE.
No, these are ordinary differential equations. These are ordinary differential. I have three particles acting on that point. Write down Newton's equation. These are Newton's equations, so that the velocity changes according to the force. The change of velocity of u, du by dt is the force, is equal to the force created by these 3 points at the center, and dx by dt, the motion forward, is u, right? But rather than moving this forward, you move the 3 red particles backward. So these are ordinary differential equations, and finitely many, because you have finitely many. So it's one, but given by finitely many sources of the force. It's absolutely clear. No partial differential equation involved. Good. And the difference between the two algorithms, so I have this tube, this Poissonian tube of radius epsilon and intensity epsilon to the minus d. And I have two algorithms, one of creating this snake and the other one of doing this. And the difference between the two, that this is forgetful. And mind that this one will not take into account all points which come in, because if a new point would come in, but it's not allowed because I'm here inside, this is the shadowing, but Chris explained you, the shadowing is also valid here. Good. Okay. And the point is whether I can say, first of all, whether I can say something meaningful about the Markov process. Second, if I can say something meaningful about the Markov process, and I tell you I can, then whether the two are close enough to infer information from the behavior of the Markovian to the behavior of the physical. Good. And first of all, what I see is the construction is rather explicit, bit complex, but well behaved. Okay, some stopping times will come in a moment. Yes. So first, the asymptotics of the Markovian version. And if there are among you some who are fans of random walks on Lie groups, then you will like what I'm telling you. Because about the Markovian version, let's see what the Markovian version does. Let me go back to the Markovian version. So this guy, this process, occasionally empties out. There are stopping times, sequence of stopping times, when there was a last red one which went out and no new red one came in. So let's define theta. It's there on these thetas. Epsilon is just telling you which process I'm looking at. Theta sub n are the consecutive following. Consecutive following stopping times that this ball is empty. There is no particle within range. Of course, you have to wait till one comes in. So since it's continuous time, it doesn't make sense to say that so wait till, so let's say it's empty, wait till at least one comes in, and then after the first time when it's again empty, right? And you easily convince yourself that these stopping times are not only well defined, but they happen quite regularly, since everything goes on scale epsilon of time. So within times of order epsilon, this will happen. Because the motion is of order, the velocity is order 1, the density of, so this is the motion, velocity, the speed is 1, the radius of the sphere is epsilon, the density of points is epsilon to the minus d. So typically you have a finite number of, a Poisson number of points inside. So indeed, within times of order epsilon, these stoppings will happen. When the stopping happens between these two, so if you look at the discrete time u, the velocity process, discretized to these stopping times, this will be a random walk on S d minus 1. So actually a random walk on, how do you call it, SOD. So if you understand well random walks on SOD, I mean the rotations of the d-dimensional space, then you can say a lot about this. And it's summarized here. There are two statements. Give me any t, no matter how large, that fixed, and look at this Markovized process. And look at this Markovized process. This Markovized process up to time t will converge to the spherical Langevin process. This is nothing more and nothing less than a central limit theorem for random walks on the Lie group SO3. Because you have this tiny, in times epsilon, you make a little change in this, right? So that means that the V process will converge to, that's exactly that content. And this is no, by the way, this is no surprise. So this is just a way of putting Castor and Papanicolaou's, say, one part of their proof. It's nothing surprising. The second statement here is, now take a sequence T epsilon go to infinity, no matter how fast or how slow, but go to infinity. And look at the displacement, not the velocity, but the displacement process scaled as you should scale it in the central limit theorem. That will converge. There is an invariance principle. Again, it follows. Here you can apply your favorite Kipnis-Varadhan type of thing. Good. So in the end, as I said, these stopping times help a lot. Not that they have, they do the thing, not only have. Good. And the point is that again, you hear the same words and in Chris's talk, no surprise. No mismatches before this time. That means, by this I mean that the snake and the non-snake, I don't know how to call this guy, which is still a snake, but it has a big head. It's a very, very thin snake with a big head. Go together up to time epsilon to the minus d plus. Sorry, minus d plus 2. I made a mistake. epsilon to the minus d plus 2. That means in 3 dimensions already to infinite time. Sufficiently infinite time. Now this is, so far I explained you what the Markovian process does. And now I want to explain the coupling, why the two things do. Why? So by the way, as Chris already emphasized, this is a probabilistic statement. This is not a statement about the physical object, because I look at the probabilistic object. If the probabilistic object doesn't do anything which contradicts physics, then I'm done. And that it doesn't do anything, I have to find a good stopping time up to which they don't mismatch. And so it's a probabilistic state. Okay, the stopping time is a complicated one. Here is it, okay, don't try to read this because formulas don't help. So take the Markovian process, as I explained, and wait till the following happens. Wait till the first time when the following happened, that in the past, say, so the stopping time is t. So t is the first time when the following happened. There exists a time in the past. Sorry, no, I say it in a different way. There exists a point in the space. There exists a point in space which sometime in the past was visited within range epsilon, was left behind. That means within range epsilon. So and revisited within range epsilon. Right? So this is my stopping time. This is a complicated one. It's not so difficult to understand what it means, but if you think about it, it's a very complex one. So I have this, because the trajectory, this trajectory is not as smooth as you see it here. So its second derivative, its second derivative is of order 1 over square root of epsilon. So its curvature is the force. The second, that the curvature of this is the typical force acting, right? And that will be of order 1 over square root of epsilon. So it's not that smooth. Nevertheless, so I travel with it. So the stopping time I speak about is the first time when I revisit a point within range epsilon, which was some time ago within range epsilon, was left behind, and again, these are decent stopping. It's a stopping time. Right? And it's very clear by construction that the first mismatch will not happen before this time. It may happen later. It's not the same as the first mismatching time. It may happen later, but because you see, it can happen. Okay, let me not do it. So certainly the first mismatch will be later than this. So if I can prove a good lower bound on this stopping time, then I'm right. But the point is that this is tricky because the trajectory is so that's what I say here, that if the trajectory is too wiggly, then imagine this is an elementary geometric problem. So if I have a too wiggly trajectory, I can immediately revisit. I can in 0 time I can revisit a point actually, if the trajectory is too wiggly. But here geometry helps. Again, as geometry helped us in the other problem, it's a different geometry problem, but it helps. Namely, by the way, of course, the handwritten part is taken from a different set of notes so what was sigma before, what was sigma this stopping time, which I'm looking for, was on this handwritten note on this page is tau. So this is sigma. What is tau on this page should be sigma on the previous pages. Sorry, I was lazy to rewrite, and I'm not that good in inserting pictures and so on. So good. As I told you, the second derivative of the trajectory is of order epsilon to the minus 1/2. Why? Because the second derivative, as we learned from Newton, is the force acting on the particle. But as we have seen, the force acting on the particle is of order epsilon to the minus 1/2. That's true in the Markovian way as well. Imagine that the force so the potential is multiplied by a square root of epsilon. And from the gradient of the potential and the fact that it's shrunk by epsilon, you get a 1 over epsilon. So anyway, the force is of order epsilon to the minus 1/2. But the ball, the radius of the ball is epsilon to the minus 1. Right? Epsilon to the minus 1. So the curvature of the ball which is traveling is much, how should I put it? Yes, that's how I should put it. The curvature of the trajectory is much smaller than the curvature of the ball which should revisit a point. This is it's a fine point actually. And this helps because this tells you that this kind of stopping time will happen as I showed here. That you indeed go away and come back. Not that if this was not the case, see, if this inequality was in the other direction, then you would see immediate revisits. Right? Okay, do it. It's a good, nice geometric problem. And using this fact, we can prove that the main proposition, our proposition that that this sigma, this is tau is what was sigma, that the probability that this stopping time happens before a time capital T is bounded above by this, and once you have that, then then the theorem follows from some union bounds. I don't say that it trivially follows, but then it follows. So this is the main. Now let's see why. Let me see how many slides I have. No, 2 more slides. The main technical lemma, and this is what I want to tell you, the main technical lemma from which this will follow is what you see in this picture. What you see in this picture is the following. You start, I speak about the Markovian process. Remember what the Markovian process is. It's complicated, but it's understandable. So it starts, so this is, say, how should I, let's say, this is the origin. It starts with velocity pointing forward. So you understand. I take a ball of comparable radius, say this is radius epsilon, this be radius 4 epsilon, but behind, and it's clear what I mean by forward and behind, by some vectorial scalar products, you can exactly say what that means. It's, let's say it is behind by 10 times the radius, and it is of radius 4 epsilon. Of course, 10 and 4, it's not important things. Then the probability that this Markovian process will ever hit back there is of order epsilon to the d minus. This is not a trivial statement. I struggled with it quite a lot. It's not a trivial statement. It's not that difficult either. At first, I thought it was very difficult, and I was stuck with it for long. But it's not so tricky. And what I want to, you are all probabilists, and as you are all probabilists here, you always think that motion is what? Brownian motion, what we learn in. So and probably you think about, many of you think about it, okay, let's say what happens if this was a Brownian motion. So say you have a Brownian, you have these sphere of radius epsilon, sphere of radius 4 epsilon, start from distance 10 epsilon, and ask about whether a Brownian motion hits back or not. And you get totally different things. So it's not, this is a non-Brownian. This process, the green process, on the long scale, long time scale is Brownian, but on the short time scale is very much non-Brownian. So it's there is a trick here. So anyway, once we have this statement and union bounds, which are cleverly put together, are not totally trivial things, then we get this proposition. And once we get this proposition, of course, we have the theorem. And I think okay, again, Green's function, we have heard from Chris that Green's function matters so much, but note that Green's function for this type of Langevin type of processes where you have velocity in the process, you have a velocity and a particle and the displacement, which is integral of the velocity. And by green function, you mean exactly the same thing. So that is the expected total times in 3 and more dimension, expected total time spent by the particle in a ball of radius epsilon. So that's how you define green function. But for processes like Ornstein-Uhlenbeck, say, that's more familiar, you are more familiar with that. Take Ornstein-Uhlenbeck, standard Ornstein-Uhlenbeck process in d dimensions. That means that the Ornstein-Uhlenbeck is your velocity process, and its integral is the position process. And write down the green function as defined. It's not a totally trivial object, so it's more complex, more complicated than the Brownian green function. And I think that I will finish now. I think I told you everything I could tell you in this talk. So thank you very much for your attention.
Well, thank you, Balint, for a really nice talk. So yeah, any questions from the audience? So feel free to unmute yourself. Or otherwise, I just start again. So maybe you can say, so you mentioned earlier somehow, if you would have the statement for all kappa, you would be close to the Holy Grail.
Yeah.
What is missing?
I would be epsilon close if it means anything.
Okay.
I would be very close, but not quite there. Not
okay,
quite
what is missing?
Sorry?
What would be somehow missing? Or you...
Look, maybe I can explain. So the statement is like this, that okay, what we want to do is the Holy Grail. The Holy Grail is the following. You see an epsilon here, but it doesn't have any role because here epsilon is kept fixed. So take just the physical process. Condition out trivial things so that you are not trapped. If you are trapped, then of course you don't expect it. So conditionally on not being trapped. The position scaled diffusively converges weakly to Brownian motion, or the central limit theorem holds for it. Randomness comes from the initial. This is what we do. Yeah? Now, the intermediate type of statement is take the weak. There is a question. So I answer this one, and then we ask Andrei this question. Just give me a sec. Take the weak coupling approximation. That means scale in, scale down. Scale in linearly, zoom in linearly, and scale down the strength of the interaction, and go as far in time. Take as long time horizon as you can take. So if this time horizon would be infinite from start, that would correspond, that would mean that you don't, so that would diminish the effect of.
Okay, I see.
So it's not the same. It's not the same. It's
Yep.
two sides of the same limit. It's not the same thing. So there is a.
Okay.
But it would be very, very long. It's beyond this kind of arguments we are doing in the joint work with Chris, and this one as well has an absolute upper limit, so beyond which I think will not work. And that was what Chris told you, that there is a time scale above which, in that case, that's the Boltzmann, that's different of this one, but in the Boltzmann-Grad case, there is a time scale that was t to the d-1, as I remember, in the Boltzmann-Grad case, that beyond that, all complexities of recollisions kick in at once. So up to that, there are slower time scales where up to lower complexity, bit higher, but still not that much, bit higher complexities come in. And there is a time scale beyond which absolutely all complexities of recollisions occur. Geometrically, there is no way of controlling it. And something similar happens here. So I think that there is an absolute upper bound. So I don't, even if ideally I could do all technical steps, which are difficult, beyond what I can do, in both cases, a an absolutely new, innovative way of approach would be needed to go beyond that absolute barrier. That's how I see it.
Yeah, makes sense. Thanks. So Andre?
Thank you. There could be many questions, several, but I would have two short. Firstly, what would happen if you would have trapping? I think this could relate to there are Bouchot trap models, right? So what would happen if you would have trapping within the process? And secondly, maybe a silly question, but could there be any, say, spherical random field, any other spherical process instead of this specific one, spherical Langevin? Thanks.
I understand. So I give you the answer to the second one. It's easy. I don't think that there is a. I think that these are the two main ones. One is a jump process. So in both cases, in these kinetic limits, you get a process for the velocity, and the velocity will be on the unit sphere for conservation of energy. And you have two. Okay, you can vary. Of course, you can give variance to each of them. And essentially, you have a jump process, and you have Brownian motion. You have Poisson or diffusive approximation or Gaussian approximation. Improbability as well. Of course, you can play with intermediate other things, but these are the essential. Now back to Bouchot. I think the Bouchot trapping model is different than this one, so I don't see the relation with Bouchot trapping. In my comments and in Chris's talk as well, trapping meant indeed that you are surrounded. There is no way out. And that's what you can have to get to not consider those cases, because that's not what we want to see.
But have you considered what would happen with trapping? Is there any, I think you had the result under the assumption.
So if you are trapped, then you are confined to a compact domain. You have a complex, geometrically complicated by compact domain, and in Chris's case, say that would be a billiard table, and that would be the ask how your particle moves on this type of billiard, with possibly scatterer inside as well, a complicated billiard. So you can ask, of course, interesting questions about ergodicity and things like that, but not scaling, because under any kind of scaling, that would be just trivial. It's not trivial in many other senses, but from the scaling. Chris, you wanted to add some comment, I think.
I wanted to ask a question, if that's okay.
It's okay for me.
Go for it. Yeah.
So you have three parameters here: the intensity, the radius, and the density.
Yeah, but phi is fixed. I also have a functional parameter. What is it?
Yeah, I agree. But if you then introduce two epsilons, you could have intermediate scalings between this and the Lorentz gas.
Between the two. That might be interesting. You are right.
And I wonder if there's a way to interpolate between your result.
Good to look at.
And then to view the Lorentz gas as the limit.
I understand what you are saying. So to interpolate between the two, that's an interesting thing. Let's speak about it. I don't have an immediate answer at all, but certainly it's an interesting thing. Yeah.
Right, sounds very good, and probably a lot of directions for future work. Indeed.
I hope that.
Indeed.
Yeah, I think these are relevant. Okay, as a last word. So these are indeed, we probabilists do a lot of things which are interesting and beautiful mathematics and so on. I speak about all of you, not myself, of course. But there are some problems which really come from true physics. So not reinterpreted, not reformulated, but truly physical. And I think these are the ones which we should keep in mind that, look, we will not be able to get to the Holy Grail, but these are our motifs, our motivating things. Yeah. Okay, so thank you very much for coming.
Yeah, so thanks again for the very nice talk. So I think if there are any more questions, we can probably.
Yeah, I'm happy to receive emails or
emails, I guess. Yeah.
Okay.
Yeah, thanks everybody for staying, and see you in 2 weeks then with the next talks on
Bye-bye.